All right, people. Hello, hello, hello. So let's check this out. Today, we're gonna begin in this unit. We're gonna be talking about solution stoichiometry. So, basically the same concepts as last unit, but now we're talking about chemical reactions that occur in water. All right, so um, basically the last reactions were just like solids with gases, solids with solids, um, and then this next chapter is all chemistry that happens in water, or things that are dissolved. The unit after that is going to be about gases. That way you kind of see a little bit of the different states of matter. Now, and before we even get started with the unit, let's talk a little bit about water. Right now, so far we haven't really talked about electronegativity, but I want to give you guys a little quick rundown on electronegativity. ptable.com, best website in the whole wide world. Now, at ptable, there's this really cool thing you can do with this website, right? Shows you this entire periodic table, and it shows you properties of these compounds, right? So if you wanted to study like a certain group, like the alkaline metals, you can see their characteristics and how they change as you go down the group, or how characteristics change as you go across. One of the main ones we want to focus on is electronegativity. Now, electronegativity, there's a pattern you must always recognize. Electronegativity increases as we go to the right, and it increases as you go up. So, fluorine has the highest electronegativity, and then francium has the lowest. All right. Now, the closer you are to fluorine, the higher your electronegativity. The closer you are to francium, the lower your electronegativity. Now, why does that happen, or what is it? Electronegativity is how much pull an atom has on electrons. So fluorine really wants to have one more electron so it can have what's called noble gas configuration, so it can look like a noble gas. We'll talk about that later, but this electronegativity is sometimes a lot of times it leads to uneven sharing of electrons, and that uneven sharing of electrons results in interesting characteristics, and sometimes even sharing of electrons results in interesting characteristics. So let's talk about water really, really quick. Now, water is H2O, as you should know, and if not, go to a different video, the first video, and start all over again. All right, so these are your H's. In the center, this is our O. So this bond here, there's an interaction between the electrons with oxygen and hydrogen. If you take a look at ptable.com and compare the electronegativity, well, oxygen's is higher than hydrogen, significantly higher. So what happens is that the electrons want to go to oxygen. So this side becomes positive, partially positive, and this side becomes partially negative. Now, oxygen and hydrogen, it does the same thing. This side becomes partially positive, and then it becomes partially negative. This right here, that's like an omega that's used, or sigma. I think that's a sigma. I don't know. I don't know my Greek letters. I just know it's the circle with the hat, or with the hair. And it's like, whatever. Anyways, what I'm saying is that this side now has drawn in all the electrons, so it's mostly negative. And it took away the electrons from those hydrogens, so those hydrogens are basically kind of positive. Now this right here shows that there's a negative side and a positive side, kind of like a little magnet, right? So now imagine you have, let's say these three. Let's erase everything. Let's keep in mind that the oxygen is negative and the hydrogen is positive. Now, let's say this water molecule, hello, I'm trying to flip it upside down. Why can't I, oh, hello, okay. Anyways, well, technical difficulties. What ends up happening is this positive part, right? These positive and these positives do not want to be next to each other. So what happens is the molecule tends to rotate so that they can line up, right? That negative is now attracted to that positive. So there's a little attraction here. And then same thing with this one. Well, now that negative is attracted to that positive, and it begins to make this crystal structure. Now, why is this interesting? Well, water is the element of life, right? Or the molecule of life. Now, water is one of the few substances that when it turns into a solid, it expands. When most things get cold, they imagine you get cold when you shrivel up. You shrivel up and you close in, and when something is hot, they expand. But water is a little funky. When it freezes, because of this attraction that I just showed you, because of those attractions, it creates space. It distances itself, so the density drops. The density of water drops, and that's why ice floats on top of water. Even though they're made out of the same thing, their densities are different because that little attraction caused water to expand. All right, so water creates this like little crystal structure, kind of like this, where it's kind of lined up, where these molecules kind of line up, and you'll see this is in 3 dimensions, so there's multiple ice cubes kind of lined up in sheets, but you see that the hydrogens are always pointed towards the oxygens, and they create this structure, right? Now, that is what happens with water on its own. Now, let's say you had salt water, right? Now, salt and all ionic compounds, remember, ionic is a metal and a non-metal. All right, so it has a positive and it has a negative, a cation and an anion. And what ends up happening here is, well, water still has that positive side and it still has that negative side. So those hydrogens end up attracting the chlorine ions, and it pulls it apart. And the oxygens, remember, the oxygens are partially negative, so they pull away at the sodium, and then little by little, they break apart your salt compounds. Now, this is a figure from your book, but basically, you have your formula unit of salt, or your large, your crystal lattice of salt, where there's a positive and negative, positive and the negatives, and water has that positive end and that negative end, and it helps break it apart and pull it apart. Now, what happens afterwards? Well, after all these water particles are floating around, and they've ripped off or they pulled apart the cations and the anions, they surround themselves and they face, so the positives will face the anions, and then the oxygens will face the cations. And you can look at the difference right here, where the oxygens are pointed to the positive, and on the other side over here, the hydrogens are pointed to the negative. So these two things right here are called hydrates. A hydrate is when an ionic compound is now surrounded by water. All right, and It's a very, very common thing to it's a very common thing that happens. And if you ever see any well, I think we've done an experiment like this, and if not, we'll do it again. The copper sulfate, when you heat it up, copper sulfate is a blue crystal, and when you heat it up, it turns white. But you add water and it turns blue again. So the water is hydrating those crystals. It's dissolving them and surrounding itself around it like that. Okay. Now, there is a limit to how much solid. I think that's enough background on water. Now, water is what you call polar. Water is what you call polar, and it's called polar because of the electronegativity, whatever I talked about earlier on. All right. Water has a bent shape. All right. A bent shape of water is caused because water has 6 valence electrons. All right. And then hydrogen has 1 valence electron. Hydrogen has 1 valence electron. They form a bond here, and these form a bond there. That looks a little ugly, so I'm just going to redraw it. But what causes that bent shape? Well, these electrons, what they do is they push down those bonds. They push them down, and it creates a little angle. And that angle results in that bent shape, or that V shape. All right. Now, I highly encourage you guys to watch this video. It's a little blurry. It's Tyler Dewitt. I used to watch him a lot growing up. But he has a very good video on ionic compounds dissolving, and then nonpolar compounds dissolving. The nonpolar compounds is a very, very good portion of the video. But anyways, one thing that I want to talk about, the like dissolves like concept, right? Water is polar, so it dissolves polar things. Or it also dissolves ionic things, right? Ionic means positive and negative. Polar means positive and negative. So they both refers to things that have charges. Now, nonpolar substances don't dissolve with water. For example, oil, all right? Oil, butter, like fats, oils, all these, you've gotten them on your clothes, whether you worked on a car or whether you've cooked or, I don't know, probably been in this class. When you get some oil on you, very hard for it to wash off. You use soap. Soap helps break it apart. But water is very, very good at dissolving things, and that's going to be our main focus for this next few sections. Okay. Farewell, people.